Hello everyone, this is the time of the class of ECE317 Digital Signal Processing. Welcome. Okay, ECE317. This is the 8th week, Monday's class. Alright, it's 8th week. We will have midterm exam on the 9th week. Okay. Midterm exam. There will be the 9th week, Monday's class. Alright, and I will give a review on the 8th week, Friday. I give a review. And the exam time, we just use the class time. That will be in the morning from 10 to 11 and 30 more minutes, so you can upload your work to the Blackboard, right? So this is the exam time, and you can find the problem in the same place with the homework, right? You should know every time where you can find your homework and how to upload the homework the same way. Now find the problem and then solve it and upload it to the Blackboard. But we have time limit, right? And I have a review. The coverage, the exam will cover, that will be chapter 2 and 3, actually from the beginning of the class. This is the Monday, the 1M, the first week Monday, until the 8th week Wednesday. The next class. Today is Monday, right? 8th week Monday, the 8th week Wednesday. So cover all the classes from here to here, and they are the whole chapter 2 and I think a part of chapter 3. Can I finish? You will see. Okay, after the Wednesday's class, so you will have all the material for the midterm exam. And today we will consider how to solve a system by Z-transform. So system by Z-transform. Right, this is also part of the exam. How to solve a system by Z-transform. The way is quite similar with the Fourier transform. We know how to solve a system by Fourier transform, right? So now you just replace the Fourier transform by Z-transform, and the feeling is like Z-transform is more convenient than Fourier transform. But the Fourier transform has a better feature for sinusoid input, right? Frequency input. Z-transform just work for in generally for any signal, in generally signal. Okay, we consider a system. So we suppose a system has a equation, which is a summation of some terms. I say a coefficient ai times y of n minus I, the delay of output, right? I run from 0 to some like m, right? M is depend, right? Depend different values. And here's I run from 0 to n, also depends on the problem. There will be bi x of n minus I. This is the equation in general form for a system. Now how to solve it? You just apply Z-transform on both sides. Then we can have summation ai is just ai constant. This delay, right? This is a shift of y, delay of y. In z domain, there will be z to negative I times capital Y of z. And this side is summation of bi, then similar. This is a delay of delay to I, then z to negative I, and then x, capital X of z. Here for the y terms, I run from 0 to m, same with it. And here's I run from 0 to n, right? This mn, same with this number. Actually, here we use a property in the table. You can find it from the table. We have any signal x of n minus nd. It is delay, right? It's a delay. Then we perform z transform. We will have z to nd, negative nd, times capital X of z. Okay, we have this one. We have this one. If you have this one in the table, just apply these, then you can have this one, right? X n minus I. This I is nd. Is this nd? And here's y of n minus I. So this y here is this x here. This signal is y, right? Different signal. And n minus I now is n minus nd. Right? Okay. All right. Then we make some change on this part, this equation. We write it as y equal to something times x. Something. This is a summation of all these bi term with z to negative I, and denominators are these ai terms, right? And times x of z. Okay, by this formula, if x is given, you can find y, right? Of course, if equation is given, x is given, then you have y. And this part, we have name of it. We call this a transfer function. Transfer function. All right, and then we can perform inverse z transform. Then we have y of n equal to something, right? Blah blah blah. Depend what are these transfer function and what are these coefficients, ai, bi, right? Now what is this transfer function, and then what is the input signal? You combine them together. You perform inverse z transform. Maybe you need to use a partial fraction, right? Then you can have y of n. You can have y of n. Summation bk z to negative k run from 0 to n, and summation k run from 0 to m. This is ak z to negative k is called the transfer function. Transfer function of the system. Sometimes people call it just a system function, and denoted as h of z. H of z. The h of z is just this one. All right, h of z. So by h of z, we have y of z equal to h of z times x of z. So here, if you know x, you know h, you can find y. And actually, this is not just used from xh to find y. You can use this formula to find any one of these three. Suppose you already know the other two. Like if you know x and y, then you have h or equal to y over x, right? Y over x. And if you know h and output, you know the transfer function, you can also have x of z equal to the output over the transfer function. you use any tool, you can find the other one. And actually these are similar in the Fourier transform. Remember, you just replace z by e to the j omega, then you have all these formulas in terms of Fourier transform. Okay, this is one thing. Here we have something more complex. You need to consider the ROC, right? Actually, when you want to find the z inverse transform to get yn, you need to know what is ROC. So here I didn't mention what is ROC, right? Okay, so for ROC, we have to consider ROC. So the thing like that, we have three formulas, right? So in each formula, like in first formula, ROC of y is a common part of ROC of h and x. Alright, and for the second things and the third one, you need to consider more complex. These two more complex because when you divide by x, the numerator will tend to be denominator, so things complex. We only in this course we only use this. We only use this one. By y of z equal to h of z times x of z, we know RC of y equal to RC of h intersection with RC of x. That's the intersection. So you need this. We need this. We use this. Alright, we use this. Then this is y. But here is still a problem. You don't know what is the RC of h. What is RC of h? So that means beside this equation, you need more information to determine the RC. You need more information to determine the RC. That information include for the RC of h. These two are different. This is for RC. I just say RC. Actually, it's for RC of y. Now, okay, of y. Put it, yeah. And now is for RC of h. RC of h. RC of h. If system is causal, RC of h is will contain like a z word larger than something, some number. Yeah, if it is causal, the RC must be z larger than some number. The number can be different, depend, but it must be larger than some number. And if system is stable, then RC of h contains all element e to the j omega, this kind of thing. Actually, this is a unit circle. In the z plane. Right. E to the j omega equal to, actually what is e to the j omega? We know this is a cosine of omega plus j sine of omega, right? So you can see you choose omega. Here's the length is 1, then this part is cosine omega, this part is sine omega, and this point is cosine plus j sine omega. So this is e to the j omega. So e to the j omega has a distance with the original point 1, right? Has distance 1 to the original point. So we have all these points with distance 1 to the original point. This is a unit circle, right? Unit circle, unit circle, unit circle. So if system is stable, the RC must contain all of these, contains a unit circle. If the RC of H, you have several possible choice. You choose the one contain the unit circle. Unit circle. Example. Let me see. Let's see. Consider y to the n 1 the 2 and a half, 2.5 y of n minus 1 plus 2.5 is just 1. This is y of n minus 2 equal to x of n. Okay. Example, we consider this. Then we can have the transfer function. There will be numerator, the coefficient here is 1, so this is just 1. Right. The denominator, the first coefficient is 1, second coefficient is 2.5, and then a power of z with a shift, so this is z to negative 1. And second is another 1 times z with the shift is here is negative 2. Alright. Then this one I can write it as 1 plus 2 times z to negative 1 and 1 plus half times z to negative 1. Okay, now we know poles. What are the poles? You see, the poles at the value of z make this part is 0. Denominator is 0. You can also see it is a number here. It should be 1 minus a pole times z to negative 1. So this is 1 minus negative 2 here. So this is negative 2. And here similar, the pole is negative 0.5. You can also use z equal to negative 0.5 here. Then you have 1 minus 1, you get 0, right? Denominator is 0. The whole fraction will be 1 over 0. That's infinite. So we call this is a pole. This is a pole, this is a pole. I have two poles. Then you see, remember last time I mentioned how to find the RC. You check the poles, magnitude of poles, absolute value of poles. I have 0.5. This is absolute value, alright, and 2. Okay, so we have 3 possible RC. 3 possible RC, and one of it contain the unit circle will be here. This is 1, right? Unit circle will be here. So I will say if we want this is a suppose this is a suppose h of this h of n system is stable. This is a stable system. If this system is stable, then if the system is stable, then RC will be has to be z, so that 0.5 smaller than z smaller than 2, okay, which contain unit circle. Unit circle. Unit circle is this one is 1. Absolute value of z is 1. Is here, right? So it is this one. If you give the whole graph of the RC, it will be like this. Here's a 0.5, here's a 2, and between them. And the unit circle is here. If here's a 1. Alright. Yeah. Okay. So like you need to check when you read the problem said, okay, you consider the system stable LTI system satisfies some equation, then you have to pay attention on this stable. This is just not one word in the first sentence. It's not important. It's very important. Yeah. If you forget this, then you don't know which will be the right RC can you choose. RC is causal, stable, and we also have third case if the system is anti-causal. Then RC must be looks like this. Z is smaller than some number. Yeah, smaller than. It's another side, opposite with the causal case. Right. Okay, this is about the RC of H. So we have three cases here. Of course, we still have another case that will be you don't need to think about it. That means the RC is given. If the RC is given, that's it, no problem. You just use that. But if RC is not given, and the problem state the system is causal, you use this kind of thing as RC. If system stable, you use this kind of thing as RC. Yeah, we can go back to the same example. If system stable and if system is causal, RC is Z larger than 2, right? Should be this way, should be this side. So totally we have three possible RC, right? And if system is anti-causal, RC is Z smaller than half, right? Smaller than half. So we have these three cases. Between 0.5 and 2, larger than 2, or smaller than half. Alright, so this is one thing we have to pay attention on the Z transform. If you use Z transform to solve the system, you have to consider that. It sounds like a little bit complex than the Fourier transform, right? Fourier transform, you just apply it, that's it. But the thing is, some case you do not have Fourier transform. And for Z transform, you can apply it all the time. This is the first one. We use the transfer function. Right? What else I can claim about transfer function? Or one more about the transfer function and the Fourier transform. Transfer function and that will be frequency response. This is h of z. This is h of e to the j omega. Actually, they are same. What do I mean? I mean this one equal to h of z provides z equal to e to the j omega. And also you can reverse the h of z. It is also h of e to the j omega. Use z to replace e to the j omega. Yeah, they are same thing. However, you need a condition. Only when this part. Only when the RC contains the unit circle. only this case. If RC do not contain the unit circle, if H of these RC do not contain the unit circle, you cannot do that. Make sense? Yeah, actually, like here you need to replace Z by e to the j omega. But if e to the j omega is not in the RC, not inside RC, not a part of RC, then you cannot change Z by this one. Z cannot equal to this, right? Yeah. So this is a condition. You can do it. You can let Z equal to e to the j omega. That means unit circle is a part of RC. Okay. This is one thing. And the second thing, to show system, we need an impulse response, right? Impulse response. So let me see. This is first. I start from where? Okay. Now see. This is 1. Yeah, we consider the transfer function stuff. Now it's 2. Impulse response. Impulse response. Impulse response. For LTI, we still use H of n to denote it, right? Let's suppose this is system. You have X as input, Y as output. If X of n is the dirt unit impulse, then Y of n is that H of n. That's impulse response, right? Impulse response. And for any other X of n, Y of n equal to H of n convolution with X of n. Okay, we have this one. This one in the frequency domain, we have by dTft, we have Y of e to the j omega equal to H of e to the j omega times X of e to the j omega. And we have this one. Then we have similar thing. I still come from here. Now by the Z transform. We still have this Y of Z equal to H of Z times X of Z. Now we still have this, just in terms of Z transform. And that's the same thing with this. Same thing with this part we just discussed. Yeah. So it's the same thing. Yeah. Same formula. This is the same formula. But now the way to reach this is start from impulse response. Now we start from impulse response. We can also have this formula. We have this formula. All right. And from here to here, in the dTft, we need to require the Fourier transform can be applied on both X and H, and sometimes we can't. And for Z transform, I will say, I think almost any time, any cases, you can apply Z transform, no matter what is X, what is H. You can always apply Z transform to get this one, Alright. This is an impulse response. And we have the third case. Solve the system. We solve the system. We need to consider, sometimes we need to consider like a sinusoid, right? Sinusoid, then what is the output? So I write in this way. Suppose H of e to the j omega, this is the system frequency response, LTI system. I write in this way. And here's X, here's Y. Right? Now this is review. For this one, we know if X of n is e to the j omega 0n, then we have Y of n equal to H of e to the j omega 0 times e to the j omega 0n. You should remember, this is very useful formula. it looks like similar with this, but different. This one is a function totally on the frequency domain. The y, capital Y, here is omega. Capital H of here is omega. Capital X of here is some omega, right? So all this formula is in the frequency domain. The omega here is a variable. The variable of frequency. It can be value run from any frequency. It's a variable. It's a variable. And this formula, it is in time domain. It's in time domain, not in frequency domain. We have omega 0 here, but this omega 0 is not a variable. This is a fixed frequency. Fixed frequency is depending on the input. Yeah, you can choose different value, but it is a fixed value, not variable, not changing variable. Make sense? Yeah, don't confuse these two. So here this is in the frequency domain. This is in the frequency domain. This is in the time domain. And this part, you compare these two. This is a function of omega, and here is a number. Or you can see this is the value of the function. This is function. This is value of the function. The function at omega equal to omega 0. Alright? You can pick different omega 0, but every omega 0 is a fixed value. Yeah, a little bit confused, but you should understand the difference between them. Okay, and if similar thing, if x of n is a cosine of some omega 0 n, then we have y of n equal to magnitude of h of e j omega 0 times cosine of omega 0 n plus angle of h of e to the j omega 0. Okay. If x of n is a sine of omega 0 n, we have y of n equal to h of e to the j omega 0 times sine of omega 0 n and angle of and phase angle of capital H at omega equal to omega 0. Alright, so we have these. This is for Fourier transform. For Fourier transform, we use the frequency response. Then we have this result, and we call this one. We call this one the eigen signal. Alright. This one, x of n, e to the j omega 0 n, is called eigensignal. Now for z transform. For z transform, we have a transfer function, right? We can write in this way. An LTI system with transfer function h of z, we can write in this way. Then we have input. Then we have output. For this one, actually we still have similar result here, but now it is write in a simple way. If x of n is some beta to the n, beta is a fixed number. Like here, that means beta is e to the j omega 0. But now beta could be any number, any complex number, any fixed complex number. Then what will be the output? What will be output? Then we have y of n. It is input convolution with impulse response, which will be summation beta to the k, right? The x of k, and h of I use h in the front. It is a summation of h of k times x of n minus k. So it's beta to n minus k, and the k run from negative to positive infinity. Alright. Okay, this one I separate. This is h of k times beta to the negative k times beta to the n, right? Yeah, this one this is one power term, right? Separate as two powers. K run from negative to positive infinite. Okay, you see, I can write it this way. All the terms contain beta to the n. Same, right? So I can move the outside of the summation. The inside summation is what? Beta, if you replace beta by z, that is z transform. In other words, you replace z in the z transform by beta, you get this one. So this is just the h of z, but z equal to beta times beta to the n. Alright? H of beta times beta to the n. Okay, we have this. Similar with this one. Input is this eigen signal. The output is still the eigen signal, but times some amplitude in front of it. And here's if input is a beta to the n, then output is just this beta n, the input, times certain constant in front of it. Right, we still have this. Okay. So in this one, it's quite similar with the Fourier transform way. But of course, here we have a requirement. We will suppose beta is an element, and this is belong. Beta belong to RC. Beta is otherwise you cannot have h of beta. You need an h of beta. Right? You need an h of beta. Yeah. Okay. We can consider an example. I can use the previous one. What is the one I used earlier? Sorry, can't find it. Anyway, I give another one. Consider y of n minus y of n minus 1 plus 1/4 y of n minus 2 equal to x of n plus x of n minus 1. Suppose we have these. If input x of n equal to equals 3 to the n, now what is output? Okay, so this case you do not need to solve the equation with so many steps. You just know there will be h of 3 times 3 to the n. So what is h? What is h of z? H of z, you look at here, it is 1 plus z to negative 1, right? This part, input side. And output side is 1 minus z to negative 1 plus 1/4 z to negative 2. And z equal to 3. This is h of 3, and times 3 to the n. Okay, just algebraic calculate, right? It is 1 plus 1/3, 1 minus 1/3, and plus 1/4 times 1/9 times 3 to the n. That's it. And if you want, you can simplify or use a calculator. Yeah, here let me simplify. This is 4 over 3, and here's a denominator. I need a 36, right? So this numerator will be 36 minus this 36 according 12 and plus 1. So it is 4 over 3. This 36 now I put in the top, right? If I move these two here, I need to turn around. And this is the whole denominator. 36 minus 12, I get 24. 24 plus 1, 25. Okay, and this 3, I got 12. So it's 48 over 12. or 25. Okay, so this is this number, and oh, I forget it. 3 to the n, 3 to the n, 3 to the n. Okay, so final answer is just this one, just this one. All right. Yes, quite simple. You just need to do this calculation. You don't need to solve the equation. And of course, if you want to consider the problem with initial condition, remember we discussed that before. If you try to solve it, consider the system with certain initial condition, then this one, it is just a particular solution. All right, this is just a particular solution. For our solutions, you need to solve the homogeneous solution, then plug in the initial, then determine the whole thing, right? Okay, so this is for the eigenfunction. Yeah, this one is also called the eigenfunction, right? Eigenfunction, eigensignal. Yeah, same thing. Signal is also function, right? Yeah, function of n. Okay, we can do some examples. So we consider example like this. I consider a system. I think I have example with and this one. Let me use this example. We consider y of n plus 2.5 y of n minus 1 plus y of n minus 2 equal to x of n. Consider this one. We want to find the impulse response. Impulse response. Impulse response. In 3 cases. The first one, causal. Second one, stable. The third one, anti-causal. Anti-causal. 3 cases. Maybe some of them they are same, but here I don't know. We just try to solve it. If they are same, they will be fine. Not same, it's also fine. Okay. So firstly, you want to find h of z. Right? The z transform, we can have transfer function. Right? Transfer function h of z will be 1 over 1 plus 2.5 z to negative 1 plus z to negative 2, and which is 1 plus 2 times z to negative 1 and 1 plus half times z to negative 1. And we can have this one. And then we can do the partial fraction. It is 1 plus 2 z to negative 1 a over it, and the b over it, 1 plus 0.5 z to negative 1. Okay, so we want to determine a and b. I have 1, this one, or equal to, you combine this together, you check the numerator, there will be a times 1 plus 0.5 z to negative 1, and b times 1 plus 2 z to negative 1. Okay, this is the same thing. If you multiply the denominator on both sides, you can also have this. You combine these 2 fractions together, compare the numerator, it is still this. Alright. Then we can have, let z equal to negative 2. I have 1 equal to a times 1 plus 0.5. Okay, z to negative 1 now is a negative 0.5, right? Yeah. And plus b times, this should be 0, because z to negative 1 is negative 0.5 times 2, you get negative 1. 1 minus 1, that's 0. So we have a is this is 1 minus 0.25, right? 0.25. So it's this is 1/4, 3/4. This is 3/4. So it's 1/3/4. So it's 4/3. This is A. And what is B? B is 1 minus A. You see, you look at it here. A plus B equal to 1. So B is 1 minus A equal to negative 1/3. Right. Okay. Now you want to find h of n. H of n, it is inverse of h of z. Then what it is, you will check the RC. But now I have 3 conditions. 1, causal case. RC of h. Yeah, you need to explain which RC. RC of h is z, because causal must be larger than something. Larger than what? You check the pole. You have 2 and 0.5. Yeah, as we did before. Yeah. So here larger than, so only larger than 2, right? That will be the case. Larger than 2 is larger than 2. And then we have h of n equal to h is larger than 2, right? So both, this is larger than 2, this is also larger than 2. So both in the positive side, right? This is a negative. A is not negative. A is 1. A is 4/3. 4/3. This is A. We see both. A is 4/3, and here's A over this one. When the RC is larger than this 2, we have negative 2 to the n u of n. Yeah, here's the negative 2, the power of negative 2. The negative, you cannot move the negative outside. It's a power of negative 2, because here is 1 minus negative 2. 1 minus negative 2. So here's a negative 2 to the n. Okay. And the second is B. B is negative 1/3, and times this part. So Z is RC is larger than 2. Now of course larger than 0.5. So this one is also in the larger side, right? So this is the case. I use a negative 0.5 to the n and the u of n. Okay, it is this one. We have the impulse response. This impulse response, it looks like it's a combine of these two. Combine of these two. When it is 0, when n is 0, you have 4/3 minus 1/3. So it is 1. Then you see, when n increase, the first one is a fraction up and down and up and down, up and down, larger and larger, right? Up and down, larger, more and more. And second is also up and down, but less values when n increase. But as a result, there will be something. Still looks like this, because this one is quite small. So roughly you can only see those values coming from here. So like this. Something looks like this. Yeah. If you want, you can try use MATLAB like a round n for the first 20s. You try this. You can have a graph look like this. Graph look like this. All right. Yeah, should be large. This, if this n is 1, this is negative 8/3. So more than 2. More than 2. All right. Okay. This side this will be 0. Okay. The second case. This is a stable case. Well, so far we already know the first case is not stable. You look at the graph, it's going up and down, and the value larger and larger, so it can be stable, right? Go to infinity out of the overflow totally. Yeah. The stable case, we want RC of h of z will contain the unit circle, so that will be 0.5 to z, then to 2, like this, that contain unit circle. Contain the unit circle. Right, contain the unit circle. So what kind of edge of n can we have? The first one is 4/3. A is 4/3. A is 4/3, and A over this one. But now the RC is smaller than 2. Smaller than 2. So we will have a negative 2 to the n and the u of negative n minus 1. Yeah, you check the table, we have that term when the RC is smaller than something, right? This is smaller than that 2. And for B is negative 1/3, and RC compared with this 0.2, it is larger than this 0.2. Larger than 0.2. Larger than this 0.2, then okay, it is just negative 0.5 to the n and u of n, right? This is the positive case. Okay, and if you want, you can have a graph. You can see when n is 0, this is u of negative 1, so it's nothing. I will say when n larger than, so this one will only contain the negative side. When n is larger than 0, include 0, this part is 0. This part is 0. Oh, I'm sorry, the time is over. Okay, that's all. Then next time let me finish. See you next time. Bye bye.